All right, I'm going to start doing the problems from section 5.5. Okay, number 1, it asks you to evaluate an integral, the integral of e to the negative x dx. And they give you a suggestion. This section is about u substitution. So for the first few problems, 1 through 6, they're helping you along and giving you the suggested u substitution. So they say that make u equal to minus x in order to compute this integral. Now, here's the idea. The idea is that the one integral that you're really good at is e to the u du. When you want to calculate this, you're asking yourself the question, what is the function or set of functions such that if you take the derivative, you get back to e to the u? Well, the derivative of e to the u is e to the u. So the thing that gets you back to e to the u is e to the u. And then you can add a constant, because if you take the derivative of a constant, that's always 0. So the derivative of this right here is e to the u, and therefore represents the most general antiderivative of e to the u. Now we're asked to do e to the minus x, and what we want to do is, since we're so good at this one, we want to convert it into that. They suggest making u equal to e to the x. What that does is it puts the u right here, and we'll have e to the u. Okay, so let's see what we have to do here. We are given this integral, and we need to convert everything in this integral into an integral with u in it. And the first step that we do after we choose our u is we take the derivative of both sides. The reason we get du here is because the derivative of u is 1, and then we add the du. If you remember from your differential calculus, this is taking the derivative implicitly. On the other side, we get negative 1 times dx. Okay, and now our job here is to substitute for everything in this integral and turn it into a u integral without leaving anything out, because otherwise we've changed the problem. We've said that u is negative x, so the e to the negative x part becomes e to the u. And then dx here, we have to find out what that is in terms of u. So for that, we solve here. This tells us that dx is equal to negative du. So when I substitute the dx in, I get negative du. What we do typically is we put the negative out in front and put the du inside the integral. Okay, now what we've got here is a negative version of the integral that I'm so good at. Okay, so the answer would be negative e to the u plus c. Okay, now what we typically do is we don't write it the way I've just written it. We just have the negative e to the u, and then when we attach a negative to a constant, well, that's just some other constant, and so we just ignore that. You could first say this is c1, and then put then negative c1, and finally my answer is negative eu plus c, where c equals negative c1. Now, if you've done any integrals, you know that you don't want to do that every single time. So I've done it once here, and now that I've done it once, I don't ever want to do it again. And so from now on, I'll just do plus c after I finish the integral. Okay, this is number 1. It's now complete. Okay, let's move on. Let's get our final answer here. As a rule, let's try to finish the problem completely. Okay, so what did we find here? We found that the integral of negative e to the negative x is equal to negative e to the negative x plus a constant. Okay, and what I didn't do in the last step there, but I just did without saying it, is that I substituted what u was originally. You see that u was equal to negative x, and so I put the problem back the way it was presented to me in terms of x. Substituting into u is just a tool to simplify the thing so that you can see what you're doing. Okay, let's move on to number 2. Number 2 is x cubed 2 plus x to the fourth to the fifth power dx, and they suggest making u equal to 2 plus x to the fourth. That's a fine suggestion. Now, the idea here is that you are really good at, you're a world expert, I hope, in fact, that's a prerequisite in order to do this problem, that you're a world expert at doing this integral. Okay, something to a power. When you integrate that, you get the power plus 1. Then you divide by that power plus a constant. And that doesn't work if you have n equals -1, because then you'll have a 0 in the denominator, so you do need to qualify that n is not equal to -1. Okay, so the idea here is you're supposed to look at this and say, oh, I'm really good when it's u to the fifth. And I know there's this other stuff here, the x cubed and the dx. I know there's that, but I'm not worried about that. What I'm thinking to myself is I'm really good at something like u to the fifth. So let's just see if we can get it into that form by setting u equal to 2 plus x to the fourth. And that's what they've suggested. So let's follow that. Say u equals 2 plus x to the fourth. And immediately, once you've chosen your u, you take the derivative of both sides. You always get du on this side. And on the right side here, I'll get 0 plus 4x to the third dx. Okay, now my job is to use this information here to do the substitution. This integral is going to become something in terms of u. I've decided that 2 plus x to the fourth is u, so that gets me my u to the fifth. Now I still need to account for the x cubed and the dx in that integral. And the way I do that is using this information. If you solve for x cubed dx, then you get 1/4 du by bringing the 4 over to the other side, or dividing both sides by 4. Okay, so now I know what the x cubed dx is. It's 1/4 du. So this integral converts into 1/4 u to the fifth du. Okay, that's a much more palatable version of this integral that we started with. I know how to do this one. This will be 1/4 times, and then the u to the fifth part will be u to the fifth over 6. I'm sorry, u to the fifth over 5. Excuse me. It will be u misspoke and then re-misspoke. Okay, you're going to add 1, u to the sixth, and then you're going to divide by that very number. Okay, so the final answer here for the u integral is u to the sixth over 24. I didn't put the plus c in, but I'll put it in now. Okay, let's go back and fix that. This is live, so I'm just going to go with whatever I'm doing here. Okay, now the last step is to put the integral back the way I found it. I'm the one who decided that u was 2 plus x to the fourth, so I got to put that back in right here. Okay, so my final answer for the integral that I was asked to compute is 1 plus x to the fourth to the sixth over 24 plus c. Okay, that's the final answer. And it would be a good idea, if you're new to this, to take the derivative of this answer and see if you get back to the thing in the integral. This is called the integrand there. The x stuff inside the integral is called the integrand, or the function inside the integral. Okay, so go ahead and do that if you are new to this, or even if you're not. Just, it's always a good idea to double check, practice your derivatives. Okay, number 3. Okay, we have x squared square root of x cubed plus 1 dx. And they make the lovely suggestion that u should be x cubed plus 1. Okay, well, what's the idea here? The idea is that if I put u equal to x cubed plus 1, I'm going to have square root of u there. Okay, can we do that? Well, that's u to the 1/2, so it falls into the same category of this right here. I can do u to a power, as long as that power isn't -1, I can do all those. So square root is just a disguised version of something with an exponent, that exponent being 1/2. Okay, let's follow their suggestion. We select u to be x cubed plus 1. The first thing we do is take the derivative, du, and on this side we get 3x squared dx. Now we're going to convert everything in this integral to something with u's. Okay, the square root part is going to be square root of u, and then I still have to account for the x squared dx, and that can be found by solving for x squared dx over here, and I get 1/3 du for that. Now I'm going to put that in, and I get 1/3 square root of u du. The design of this is to think of square root, and you should be kind of always keeping that in the back of your mind, that the square root is really a half power, so this is the same as u to the 1/2 du. This is Robert. This is Bob. Same guy, different name, different symbolism. Okay, well, how do I do u to some power? I'm a world expert at that. All I do is add 1. 1/2 plus 1 will be 3/2. Then I divide by that very 3/2. Now, when you're dividing by a fraction, that's the same as multiplying by the reciprocal. Okay, so let me go over here on the side. It's u to the 3/2 divided by 3/2. But how ugly is that? We don't like to have a fraction within a fraction. Okay, so what we do is multiply top and bottom by 2. And that cancels the 2's down here, and I end up with 2/3 u to the 3/2. So you see, dividing by 3/2 is the same as multiplying by the reciprocal. Okay, I've got my constant here. Then I'm just going to do a little housekeeping, and I get 2/9 u to the 3/2 plus c. Then, of course, we have to put things back the way we found them. U is x to the x cubed plus 1, so let's put that back in. This is 2/9 x cubed plus 1 to the 3/2 plus c. That is the answer. And I also recommend that you take the derivative of that and see if you get back to the original answer. You will. Okay, number 4. Okay, now the book is engaging in a little bit of confuse the enemy tactics. All of a sudden they switch to t instead of x. Well, we are not going to be fooled by that. After all, we are so comfortable with variables that we're switching into u. So t is not going to throw us off. Okay, their suggestion is that u equals 1 minus 6t. And the idea is that in the back of your mind, you are really good at this integral. You're a world expert. As long as n is not equal to -1, it's just add 1 to the power, divide by that number, and you're home free. Okay, so what we're really thinking of here is that this is one of those. It's the same as 1 minus 6t to the -4, because a power in the denominator is the same as a negative power in the numerator. So these two integrals are the same thing. I've just written them differently, but the idea is to then pick this part as u, and then I have u to the -4. Let's see how it works out. If I pick u equal 1 minus 6t, then du is 0 minus 6 dt. So now when I convert this integral here, I get, on the bottom, I have u to the 4th. And now I have to account for the dt. dt is equal to -1/6 du. So I put that in. I have a negative 1 over 6, and then a du. Put that in the numerator. Now I prefer to look at it like this because that's how I'm thinking of it anyway. It's u to the negative 4 du. Okay, so now when I add 1, I'm going to get to negative 3. So negative 1/6, that comes along for the ride. And then I get u to the negative 3 divided by that same negative 3. Because I'm adding 1, right? The antiderivative of u to the n is u to the n plus 1. When I do that, I get negative 3 there. Okay, let's do a little housekeeping. The negatives cancel, and I have 1 over 18 u to the negative 3. Now let's put things back the way we found them. So this is 1 over 18, and then I have u to the negative 3 is 1 minus 6t to the negative 3. And we don't usually like to write things with negative exponents, so let's write it now like 1 over 18, 1 minus 6t cubed. Plus c. Forgot my plus c in there each stage. Okay, we'll go back. Put that in. Okay, moving along. Number 5. Now, at some point, I guess I should check and see if somebody's actually watching. I doubt it, because I'm brand new, but, well, you know, I know that. Okay, there we go. This is for all 0 of you. That's fine. I don't mind doing this for nobody, because after all, it's going to be up there for all of eternity. Okay, number 5. Oh, wow, we're getting into the trig functions now. Cosine cubed theta, sine theta, d theta. Okay, well, there you go. The variable is now theta. Notice that when the theta is the variable, then you're going to have a d theta. In the previous one, when the variable was a t, then you have a dt. And when we switch it to a u, you got a du. So this right here always has to match the variable in the integral. All right, well, here I see a power again, and we're getting so good at powers. Remember, I'm super good at this integral, and you are too, I hope. So just hoping, right, praying, if I want to get it to look like this, I might as well pick u to be cosine theta. It may make that suggestion in the problem, but I'm just giving you the thought process. As soon as you pick your u, you take the derivative, du on the left side, and remember the derivative of cosine is negative sine theta, d theta. When I convert this integral, I want to account for everything I see. The cosine theta is going to be u, so I have u cubed. The sine theta part, sine theta d theta, that can be found right here. Sine theta d theta is equal to negative du. You don't have to write this out every time. You can do it in your head or whatever level you're comfortable with, but I'm writing it out so you see what I'm thinking. Okay, that's the conversion. And then I'm so good at that, I'm feeling good about this now. This is negative u to the 4th over 4 plus a constant. And then we'll be so kind as to put that back the way we found it. The way we found that is where u is equal to cosine. So that'll be cosine to the 4th theta plus c. Number 6, this brings us to the last one in this section. They're going for a little bit of the old confuse the enemy. because often these problems are kind of absurd in how they're presented, but it's really just it has to be rigged a certain way so that the integral can be done. But then it also, it gets you where you have to get comfortable seeing all kinds of crazy notation. And this one's a good example of that. Who likes secant, right? Who likes 1 over x? Who likes the integral? Who likes a fraction with all that involved? Who likes it all squared? Okay, so there's a lot of stuff going on in here. Luckily for us, they make a suggestion. They say, well, let's let u equal 1 over x. And what is their thinking? Well, one of the integrals that you know how to do, that you're a world expert at, is this integral. Because secant squared is a known derivative of something. The something is tangent. So since the derivative of tangent is secant squared, a lot of times you see secant squared in integrals because that's a known antiderivative, right? You see how rigged it is? And it wouldn't be secant cubed. It's got to be secant squared because that's the one we know. And since you know it, you got to say to yourself, geez, I know this looks complicated, but boy, wouldn't it be great if it was just secant squared u? Because that's the one I know. And the way to get that is to pick u to be 1 over x, because that's how I'm going to end up getting secant squared u, right? Putting it right there. Well, they make that suggestion anyway. And when you pick your u, you immediately take the derivative. Now you have to take the derivative of this properly. Hopefully you're proficient at that, but let's remember that this is really x to the negative 1. And so when you take the derivative, you multiply in front by the negative 1, and then you subtract 1 from the exponent. That would give me negative 2 as the exponent, which is the same as 1 over x squared. Dx. Okay, well, I'm hoping to convert this integral into something that I'm able to do. I know that I'm going to have secant squared u because, after all, I picked u to be 1 over x right there, so I'm going to put that in. And then I have to account for this other part of the integral, and that's 1 over x squared times dx. And look at what, it's like a miracle. It's right there. It's right there. Look at that. So look, 1 over x squared dx, well, that's minus du. And now I've accounted for everything. I have a minus there, I have a du, and look, it's that integral that I know how to do. That's going to be negative tangent of u plus a constant. But then, of course, the problem wasn't presented to me in u, so I have to put it back the way I found it. I decided that u, or the book did, u was 1 over x. So I'm going to put that in for u, and then I'm done. So this nasty looking integral, secant squared of 1 over x squared dx, that's minus tangent 1 over x plus c. And look how rigged it is, folks. Look at that. They put the secant squared, and then whatever they had here, whatever they put here, look at that. They put the derivative of it there so that when we did our u substitution, it was all ready to go. Look how rigged that thing is. That's rigged. All right. So here we go. Now they're just dropping you in the middle of the ocean and saying, try to find land. No help, just a big pile of integrals. So here we go. X sine x squared dx. I mean, they're just tempting you, right? Do you know the thing whose derivative is sine? Do you know the integral of sine u? Well, yes, the thing whose derivative is sine, that would be minus cosine, because the derivative of cosine is negative sine, and I don't want that negative, so the derivative of sine is negative cosine u plus c. Okay. Well, let's try it out. let's say u equals x squared, because I want sine u. But as soon as I pick u, I'm going to take the derivative, 2x dx. Derivative of x squared is 2x. Put the dx in there. And now I need to account for everything I see. The x squared is going to be u, so that's sine u. And then the x dx that's left over, I get that right here. Look at what a miracle it is. It's sitting right here. X dx is equal to 1/2 du. So we put the 1/2 out here, put the du, and that's that integral I'm so good at. I get negative 1/2 cosine of u plus c. But then, of course, we have to put it back the way we found it. So negative 1/2 cosine of x squared plus c. Okay. Now I want to offer you a little bit, I don't know if it's more advanced, but I guess it would be, but it's another more intuitive way to approach this. Same problem. I mean, we're gonna just redo it. Okay, let's say we get this, okay, given to you on a test or get it in the book, and you say to yourself, well, I need to get the antiderivative of this. But couldn't you also say that, well, the only way I could take the derivative of something and get sine x squared is if I had cosine x squared, right? That's sort of a good guess, right? That's a good guess, because to take the derivative of something and get something that has sine x squared in it, well, I better have had cosine x squared, right? That's how you get it. Now, if I thought that was my answer, right, I should check it. And when I check it, what I get is, see, if I take the derivative of this, I get, well, using the chain rule, I get negative sine, x squared times the derivative of x squared, which is 2x. Okay, so then that gives me negative 2x sine x squared. Oh, shoot. Well, see, what I wanted to do when I got back, I wanted to get back to this right here, and it's got this pesky negative 2. Oh, well, here's what we do. Let's just multiply both sides by a negative 1/2. So if I go negative 1/2 cosine x squared and take the derivative of that, well, then I would have just x sine of x squared. And there's my answer, you see. If you can kind of guess it and then check it and see how it's off and then adjust it. Okay? So that's a way that you can start learning to do these integrals in your head. I say to myself, oh, it's got to be cosine x squared. There's no other way to get that. Oh, and look, I've got this convenient x there, because when I take the derivative of the 2x using the chain rule, right, there it is. But when I'm going to get a 2, I need a negative 1/2 to cancel. I'm going to get a negative from the cosine and a 2 from the x squared. Okay, anyway, let's move on. I'm going to try to add that to some of these integrals to start to get you to be able to do integrals in your head. And when you start to be able to do that, then you start to see how rigged they are, how they're set up to be integrated. They have to be a certain way. Okay, we're on number 8 here. X squared e to the x cubed. Oh my goodness, how rigged is that? So what I say to myself is, I mean, I love e to the u, right? I'm so good at e to the u du. So if I want e to the u du, well, I better pick u to be that thing right there, because I'm so good at that. I'm not worried about the other stuff. I'm hoping that they rigged it so it all work out. Okay, so I'm going to start off with that. U equals x cubed. Great. And then every time, take the derivative immediately. Du on the left side, 3x squared dx. Okay, now I want to convert this, and I got to account for everything. Can't change the problem. The e to the x cubed, that's going to be e to the u. And I still have to account for the x squared dx. And look, oh my God, it's a miracle. It's right there. X squared dx is 1/3 du. Perfect. I'll put that in. I got a 1/3 and a du. I'm so good at this integral. I get 1/3 e to the u plus a constant, and then I'm going to put it back the way I found it. U is x cubed. Okay, now you could also do this integral in your head. Leave it or else. So you say to yourself, if I have to find something that when I take the derivative I get back to this monstrosity, well, it better have had e to the x cubed in it, because when I take the derivative of e to the x cubed, I get e to the x cubed back. I get some other stuff, but I'm definitely going to get e to the x cubed back. Well, what happens when I take the derivative of that? I get e to the x cubed times the derivative of x cubed, which is 3x squared e to the x cubed. Well, geez, that's an awfully good guess, because look, I almost got it. I got this pesky 3 though, right? So what must be the answer? If I multiply both sides by 1/3, I'll have the derivative of 1/3 e to the x cubed is x squared e to the x cubed, which is what I wanted. You see? So, and you don't have to write this out. This doesn't have to be written out. Maybe the first few times, or maybe the first 20 times, I don't know, but you got if you write it out a few times, then you can start to do this actually in your head. You start to reason it out. Well, what would it have to be? If there was this function where I took the derivative and got back to that, wouldn't I have had to have had an e to the x cubed? Well, what does that give me? Shoot, it almost gives me exactly what I need, except for the 1/3. Okay, so I want to try to get you guys to think that way. Some of you are not going to be comfortable with that, and that's fine. Just let it go. Others of you are going to like that and want to start to do some of these things in your head, because it gets a little tedious when you write this stuff out. Okay, number 9. Got 1 minus 2x to the 9th power. And so what I say to myself is, geez, I wish that was u to the 9th, because I am so good at that. And in order to get there, well, I would have to pick u to be 1 minus 2x, because then I'd have u to the 9th. When I take the derivative, I get negative 2 dx, and then I want to convert this integral, so I get u to the 9th, because this goes right there for u, right? The u is going to be right there. And then I have to account for that dx. There it is right there. Dx is negative 1/2 du. Again, you don't have to write that out. I'm writing it out for you, but you can just do that in your head. And so dx is going to be negative 1/2 u to the 9th du. All right, I'm ready to go. It's negative 1/2, and then the antiderivative of this is u to the 10th over 10. Plus a constant. Do a little housekeeping. I have u to the 10th over 20, and then we'll put things back the way we found them. That would be negative 1 minus 2x to the 10th over 20 plus a constant. Again, we could just do that in our head, because what we had was 1 minus 2x to the 9th. And you say, well, geez, if I had to have something and I took the derivative and I got 1 minus 2x to the 9th, wouldn't I have had to have 1 minus 2x to the 10th to get there? So that's probably a good guess. Let's try it. Let's say, what if I had 1 minus 2x to the 10th and I took the derivative of that? Well, then I would get 10 times 1 minus 2x to the 9th times the derivative of the inside using the chain rule, which would be negative 2. And so that would give me negative 20, 1 minus 2x to the 9th. Oh, shoot. I wanted to get just 1 minus 2x to the 9th. But I got this pesky minus 120, minus 20. So let's just bring it over to the other side. And so negative 1 over 20 times 1 minus 2x to the 10th. The derivative of that must be 1 minus 2x to the 9th. And there I was able to just because I'm good at derivatives, I can figure out what the antiderivative just by thinking about what it would have to be. Okay, that you can start to do that in your head. I know it. I know some of you are ready, and some of you are not, and that's okay. And some of you will never want to do that, and that's okay too. So you can just ignore me when I do that. When I go and do that annoying in your head stuff. The idea here is to get good at integrals. We want to kind of get into the how they're built, and then you can kind of anticipate. Again, we've got to confuse the enemy situation, but we will not be confused. First of all, they use t. Oh my goodness, we use t instead of x. What are they doing to me? And then they've got this 2.4 there. Wow, doesn't that just make your eyebrows raise? What are we going to do? Well, it's just a number. I can do anything. U to the n du. I'm good at this as long as n is not equal to -1. That's equal to u to the n plus 1 over n plus 1. And n could be 2.4. It's fine. It just looks ugly. So we'll let u equal 3t plus 2. du is 3 dt. Let's account for everything we see in this integral. Okay, I've got u to the 2.4. Now I have to see what dt is. dt is equal to 1/3 du. Let's put that in, 1/3 du. All right, now this is not very comfortable because I got to add 1 to 2.4. I know that's 3.4, but then I got to divide by it. It's not very nice, but let's just do it. Okay, that's what the decoder ring says to do. It's going to be u to the 3.4 divided by 3.4. Plus c. Now, it depends on how much you want to go through this, but u to the 3/4, well, that's 1 minus, oops, sorry, doing the previous problem. Okay, that is 3t plus 2 to the 3.4 power over 3 times 3.4. So I guess that's 10.2. Yeah, well, let's go. Let's do a little baby math here. So 10.2, that's 10 and 2/10, which is if I want to make one fraction out of that, that's 10 times 10 is 100 plus 2 is 102 over 10, and then we can reduce that. That's 51 over 5. Okay, but that's all in the denominator, so we could flip it around, and then that would be 5 over 51, 3t plus 2 to the 3/4 plus c. I haven't looked to see how they present it in the back of the book. Well, actually, they don't. I'm lucky. Number 10, it's even. They don't present it in the back of the book. Anyway, if you like, if it really bothers you to have decimals like that, you can convert this into fractions at the beginning because that's 2 and 4/10, which is 24 over 10, which is 12 over 5. So you can make it 12/5 as a fraction. Do it that way if you like. Okay, enough of that. But again, they're just putting that in there to just put whatever they, anything to make it look different in the exponent there. But we know how to do that. It's always just u to the n plus 1 over n plus 1 as long as we don't have that special case. Okay, I'm going to stop because this is my first stream since I really feel like I got the bugs worked out, and I want to stop and check that it worked, and I don't think anybody's watching anyway. So I'll just post this, and I'll be around in the next stream.